Thank you once again for coming back. So this video we are going to be talking about approximation techniques of integration of finding areas underneath curves. So we're going to kind of go into depth about how we can define what an integral is. So, and then afterwards we're going to go into the fundamental theorem of calculus and then work backwards and then define definite integrals and indefinite integrals. Okay, so let's start off with some function. And we want to find the area underneath this curve from x is equal to 0 to 1, 2, 3, 4. So this technique is actually what graphing calculators and just about any programs that numerically determine area underneath the curves use. So first, what we're going to do is take a look at rectangles. So we know area of a rectangle is equal to length times width. So something that we can do is approximate the area of this by finding rectangles that are approximately so here we're kind of going to overshoot, so we can also undershoot as well. And then we can find averages. However, something that would be better is to make our triangles smaller. So let's kind of get rid of some of these triangles. Not triangles, rectangles. Let's just redraw this function. So we have this function. Okay. So let's make the lengths smaller. Here we can see that our area is actually getting a lot better, and we can further make these rectangles smaller. And further improve our accuracy until we get to this point. So let's just rewrite this. So we're 1, 2, 3, 4. That's how far we want to go. Until we get to the point where the rectangles, the height of the rectangles matches the function. And it looks like we have the entire area just shaded in. So if you've ever seen your graphing calculator when you do an integration, this is what it looks like. And that's really what it's doing. It's putting in many, many very thin rectangles into this function and adding the areas of these rectangles together. So we're going to very quickly define this. So here, the area of a given rectangle, I. So we're going to call each rectangle I is equal to, okay, so let's call the width f of xi, and the length some delta x. Delta xi. And something that we're going to go into a little more depth to later on when we're going into summing sequences and things like that is summation notation. So I'm just going to very quickly define summation notation. So we use the uppercase sigma. So let's just look at the notation here. So basically what this is saying is it's the sum of all values within this bracket from I is equal to 0 to n. So you can choose to leave out I equals n, or you can just leave the I equals n. So this is a typical notation where you just leave the n on top. So here basically what we're doing is summing all the area of the rectangle. So let's just define AI is the area under rectangle I. So we're summing the areas underneath the rectangle I. So that's equal to the sum I equals 0 to n of f of x I delta x I. Okay, so now we have to add one extra term because we have this delta x which we haven't defined. So delta x, say we have delta x is equal to 1. In this case, if we have delta x is equal to 1, we have 4 possible terms. So we have, so if we have 1 and we're summing to 4, we can have 4 possible rectangles. If we make this 0.1, we have 40 possible rectangles. If we have 0.01, we have 400 possible rectangles, and so on. So we want to add a limit term. So limit as delta x I approaches 0. And now let's just make an assumption that all delta x i's are equal to each other. So we can bring the limit, because it's not within the sum, we can bring the limit outside. So it's limit as delta x approaches 0 of the sum I equals 0 to n of f of x I delta x. And this is equal to I, which is equal to the area. Okay. So, now, from here, let's also introduce some new terminology where an elongated s is defined as an integral. And let's introduce also AB. So this would be the integral from x equals a to x equals b. So in this case, a, b, f of x dx is equal to the limit as delta x approaches 0, the sum now just one more minor technicality, because we are approaching 0 with the delta x. The number of n is proportional to 1 over delta x. So as delta x approaches 0, we can turn this to an infinity. So we're defining the integral as the integral of f of x from a to b is equal to the sum of the area of the rectangles. And this will provide the basis for the fundamental theorem of calculus, which essentially states that the value of f of b, so the capital F of b minus capital F of a, so b is located here and a is located over here, is equal to the integral from a to b of f of x dx. And we're going to go into a little more detail about this later on. So just to sum what we did in this video, to summarize basically what we did is we have defined the integral. So we have defined what an integral is. The integral is the area underneath the curve. So in order to summarize in order to determine what the area under the curve is, you have to take an infinite amount of very small rectangles and find the area of these infinitesimally thin rectangles. And that's essentially what we're doing, because remember, f of x, I is y, and this is our x term. So this is our width term, and this is our length term. So, once again, thank you for coming back, and I look forward to seeing you again soon.